our final lesson of this unit, we're going to look at something called inverse functions. Essentially, the inverse of a function is what happens when you take all of the x values of a function and trade them with whatever the y values were. So let's suppose we have this function here or with these three different points, 1, 0, negative 3, 5, and 0, 4. Well, the inverse of that function would be if I just took all the x values and switched them with what the y values are for each point. So 1, 0 would turn into 0, 1, negative 3, 5 would turn into 5, negative 3, and 0, 4 would turn into 4, 0. On a graph, it would look like this. So if I plotted 1, 0, which would be right here, negative 3, 5, which would be up here, and 0, 4, which would be right here, the inverse function, or the inverse of each of these points, would be 0, 1, 5, negative 3, and 4, 0. So, looking at these points and where their inverse was, it's almost as if they were reflected over this diagonal line right here. Now, this diagonal line has an equation that we know. Do you know what the equation of this diagonal line would be? Well, everywhere on this line, notice how the y value is the same as the x value. So right here, the x value is 1, the y value is 1. Up here, the x value is 3, the y value is 3. And same thing, down here, the x value is negative 4, the y value is negative 4. So essentially the y value is always equal to the x value on this line, so we get the equation y equals x. So inverse functions happen to be reflections over the line y equals x. And just to clarify our definition here, the word inverse to us means opposite or reverse, but in the case of talking about functions, it's just more specific. It just means we're going to switch the x values and the y values in all the points. Okay, let's look at some other notes on inverse functions. We do have a special notation that we use. Remember, when we talk about functions, we use our function notation, f at x. Well, when we talk about the inverse of a function, we have a special notation for that as well. And it looks like this. It looks like there's an exponent of negative 1 above the f. But we just read this as f inverse of x. We don't make it 1 over f at x or anything like that. Remember, it's just a notation. Just like how up here we're not multiplying this f times that x. This is the notation we're going to use when we want to say that it's the inverse function of whatever we started with. So f inverse of x. So how do we turn a function into the inverse of a function? Well, there's a few steps that we're going to take. The first thing is, if we see that a function is written with function notation, so f at x equals something, let's see here, let's make up an example here, f at x, and I'll just do a linear one to make it easy. So, I don't know, 3x minus 5. Okay, so let's say we had a linear function, f at x equals 3x minus 5. So step 1 would just be to replace the f at x with the letter y. We're going to change it into xy notation. And of course we know that f at x is the same thing as just writing y. So these things are equivalent. The next step is I'm going to switch the x's with the y's. So wherever you see y, I'm going to turn it into an x, and wherever I see x, I'm going to turn it into a y. So I'm going to say, for the inverse, x is going to equal 3y minus 5. Now it doesn't logically make sense for this equation to equal the equation right below it, so we have to sort of indicate that we're going to be talking about the inverse right now. So off to the side, or right beside this line that I switch the x's and the y's, I'm going to put this little box right here. I'm just going to write I and v. And what this tells me is now I'm figuring out the equation for the inverse instead of rearranging this original equation of our function. So I'm going to write the little I and v. That tells me, again, that I'm now trying to figure out the inverse. Step 3 is now I need to solve for y. Remember, we always wanted, in function notation, is always f at x equals, or always y equals something. So let's rearrange this equation for y. So our first step is going to move the negative 5 over to the other side. So I'm going to get x plus 5 is equal to 3y. And then I'm going to divide by 3. So I'm left with y is equal to x plus 5 divided by 3. And there's our new function. Now, remember though that this is the inverse of our original function. So step 4 is I want to write my final answer in inverse notation, or using inverse notation. So I'm going to replace this y now with the inverse notation, f at negative 1, but we say f inverse at x equals x plus 5 over 3. And there you have it. Our original function, f at x equals 3x minus 5. The inverse of that function is f inverse at x equals x plus 5 over 3. Now, looking at these two functions, the first one was linear. Is the second one linear as well? Can you figure that out? Well, in fact, it is linear. It has a slope here of 1/3, and it has a y-intercept of 5 over 3. All right, let's see a couple more examples. So for this example, we're going to find the inverse function, and then also state the domain and the range of both my original function and the inverse function. So here's part A. F at x is equal to x squared plus 3. Now, if I were to draw a quick sketch of what this would look like, maybe you can figure this out too. Draw my little x, y axes here. What type of parent function do we have? Well, because I have the x squared, obviously now this should be a quadratic, and the only transformation that's occurring on it is it's moving up 3. So if I were to draw or sketch what this would look like, it would probably look something like this. My original parent function starting down here, but the vertex is now 3 higher than before. And I'm going to do a little trick here. I'm going to move this point over to there. That'll help me out. So if I were to now find the inverse. So let's remember, step 1, I want to take f at x and change it into y equals. Remembering that f at x is just the same thing as writing y. Next, I'm going to switch wherever I see a y into an x, and wherever I see an x into a y. So x equals y squared plus 3. But also remembering that I have to write inv and put it in a box, just to tell me that I'm working on the inverse function now, not the original function. Make sure it's on the same line too, so you don't get confused. Step 3 is to solve for y. So to solve for y here, I'm going to move the 3 over to the other side. So x minus 3 equals y squared. And then to get rid of the squared, we square root both sides. So I'm going to end up with y equals the square root of x minus 3. And last but not least, this y I need to change into the inverse function notation. So f to the exponent negative 1, but we read it as f inverse of x equals the square root of x minus 3. Now, if you've been paying attention, maybe you've seen that I've omitted something in here, but I'm going to sketch this out first, and maybe you'll catch on to what I'm missing. Okay, so what does this inverse function look like? Well, it's the radical function, but x has moved right 3, which means all my x values have moved right 3. So instead of starting at 0, 0, I'm actually starting 3 over, and now my function moves up like this. Okay, so this is at the point 3, 0. And that's this function right here. But if we look at our original function, my original function is a parabola. So what happened to this other arm of the parabola? Because when I write my inverse function, which is the radical function, I only get one bar here. So what do I need to adjust to this equation so that it represents not only this bar, but I could also draw the other bar down below? Well, remember, when we take the square root of something, the answer is always positive and negative. Like the square root of 25 is positive 5 and negative 5. So I have to put a plus and a minus in front of the square root. And what the minus does is it reflects it over the x-axis. So this here would also be reflected in the x-axis and then appear down here. And there you have it. This is f inverse at x, whereas the original one up here was just f at x. And let's just prove here that this is a reflection over the line y equals x. So I'm going to draw a little green line that goes through here. And you can see that if you tilt your head, one is a reflection of the other one. So indeed, this is a reflection over the y equals x line. Now you don't have to draw this line in, but just to show you that it is. Now step 2 here is I need to state the domain and range of each. So the first one should be easy. I'm going to do it in blue. So the domain of f and x, well, it's just a parabola that has moved up 3. So my domain, or the possible x values, could be anything in the real number system. Whereas my range, which is the possible y values, well, 3 is the lowest it can be, so anything 3 or above. So I'm going to start by saying that y has to be, or all the y values are members of the real number system, but y also has to be greater or equal to 3. All right, what about the domain and range of my inverse function? So what's the domain and range of f inverse at x? Well, just look at the graph and it'll help you out. The domain, well, x values start here and then move to the right. Nothing goes to the left of this point right here, which is at 3. So it's like I say x ER, and x has to be greater or equal to 3. And what about the possible y values? Well, look at the graph again, and we see that y extends going onwards, upwards from here, and it goes downwards from here. It'll eventually hit every single y value, so all I have is YER. And I want you to look at the domain and range of both of these functions, and what do you notice? Well, just like how all the x's switch spots with the y's, and all the y's switch spots with the x's, the domain of the original function turned into the range of the inverse function, whereas the range of the original function turned into the domain of the inverse function. So those things switch spots as well. The only thing that really changed was, instead of writing XER for the domain here, I have to write YER for the range. And same thing, the range here is YER slash y is greater than or equal to 3. Down here it's XER and x is greater or equal to 3. But those things just switch spots. And that you'll always find that's true with inverse functions. So naming the domain and range for inverse functions should be an easy task and basically equal to free marks on a test. Here's our second example. So let's take h at x here and find the inverse. So again, step 1, we want to start by writing y equals instead of the function notation h at x equals. Our next step is to switch the x's with the y's and vice versa. So it'll read x equals the square root of y plus 4. And remember, I have to write here that I'm now working with the inverse function, so I'm going to put that in a box over here. To try to get y by itself, my first move is I need to get rid of this square root, so I need to square both sides. So this will be x squared equals y plus 4, because the squared on this side just gets rid of the square root function. And then I need to move the 4 over to the other side. So I have x squared minus 4 equals y. And writing it in inverse notation because I'm using h instead of f, so I write it as h inverse at x is equal to x squared minus 4. So drawing the sketch of these things, I'll quickly draw a sketch here. I'll use some lines to help me out. Oops. Okay, so the original function here is the square root function, but all the x values have been moved to the left 4. So that'd be like if I went from here and I came up like that, and this is at the point negative 4 and 0. And if I draw my line here going through our y equals x line, you'll see that I should have something that is sort of mirror imaged of this. So what do I have? Well, I have a parabola that has gone down 4 units. So in blue here, I'm going to draw that going down 4 units. So right around here. And a parabola will go up like this, which looks mirror image to that. But a parabola also goes around the other side too. So I'm just going to draw a little dotted line here going up this way. It doesn't look dotted when I draw it on the tablet here, but we have an interesting situation. My original function only existed up there, but my inverse function, it looks as though it exists 2 arms worth. Well, that can't happen. My inverse function needs to have the same line reflected. I can't add in any line based on it. So this is going to be where our domain and our range come in. So I'm going to get rid of that dotted line there because I don't want it. I only want this line right here where this is at the point 0, negative 4. So when we do our domain and range, it's going to be very important. So let's do the domain and range for our original function here, h. So the domain, x, er, and the x values have to be greater or equal to negative 4. My range, well, notice I have nothing below 0. So I have er, and y has to be greater or equal to 0. So now for the inverse function. Remember, they're just the opposite of what you saw above. So my domain is the same as the range, but we changed the letters from y to x. So x, er, and x has to be greater or equal to 0. And that makes sense, right? You look at the graph, notice how all of my x values start here and then just continue out that way. And my range, well, y, er, and y has to be greater or equal to negative 4. And there you have it. Okay, one final example that we're going to show you. What happens if I want to find the inverse of something that looks like this? F at x equals 2x squared plus 16x plus 29. Well, this is a quadratic function again, but it's written not in vertex form, but in standard form. So it works a little bit differently. Let's see. So step 1, I want to again change from f at x to y equals. So let's write this as y equals 2x squared plus 16x plus 29. And now I want to change. So to continue, because I have an x squared here and an x, I don't want to switch all the x's and all the y's yet. Because I don't want to have a y squared and a y. That is too hard to isolate for. So in order for me to only get one x on this side, do you know how I change the format? Well, if you guessed that I have to complete the square, you'd be absolutely right. We need to get this written in vertex form so that we can find the inverse. So let's do that. So let's complete the square here. So remember, step 1 here is to take whatever number's in front of the x square and factor it out. So I'm left with 2 outside, and then x squared plus, we factor out a 2 from here, and we leave the plus 29 out on its own. The 2 will stay out here the entire time. I complete the square in the middle, so 8 divided by 2 is 4. 4 squared is 16, so I have x squared plus 8x. And then I add a 16 and I subtract a 16. Next, I complete the square. So I take the first 3 terms, x squared plus 8x plus 16. I just divide this number by 2, so 4. So I'm left with x plus, because this sign's plus, 4 all squared. This 16 has now left the bracket, so I need to multiply it by 2. So negative 16 times 2 is negative 32. And then add the 29. And we can see that negative 32 plus 29, well, we're just left with a negative 3. I'll just fix that up there. So my final equation here, y equals 2 bracket x plus 4 all squared, and then minus 3. Now this is way easier to find the inverse of, so let's do that. I'm going to write my little inverse box here. Change all the y's for x's. So this is now going to equal, or sorry, be x equals 2 bracket y plus 4 all squared minus 3. Isolate for y, so you're going to do backwards bedmass here. So move the negative 3 over to the other side, so we get plus 3 over here. Next step is to divide both sides by 2. So I'm going to have x plus 3 divided by 2 all equal to y plus 4 all squared. Next I got to square root both sides, so I'm left with excuse me, square root of x plus 3 divided by 2, remembering that it's actually plus and minus, equal to y plus 4. And last but not least, I now move the 4 over to the other side. So I get negative 4 plus or minus the square root of x plus 3 over 2. And that equals y. So from here I'm going to write this in my inverse function notation. So f inverse at x equals negative 4 plus or minus the square root of x plus 3 over 2. Very easy once you've completed the square and gotten it into vertex form. And there you have it. From here we could figure out what the domain and the range is based on where my vertex is. I know that my vertex is at negative 4, negative 3. So if I were to draw a quick little sketch here, draw my axes here, I've got my vertex at negative 4, negative 3. So negative 4, negative 3. I know that I'm opening upwards because there's no negative sign there, so my original parabola is going to look something like this. This is at negative 4, negative 3. So what's your domain here? Well, my domain here is xer. My range is yer, and y has to be greater or equal to negative 3. So what would be your domain and range for this inverse function? Well, the exact opposite. So the domain is xer, and x has to be greater or equal to negative 3, and the range is yer. So when you come to class tomorrow, we're going to go over one more question, which is more of a word problem. But the homework questions are posted on your unit outline. So try those out tonight if you have some time, or bring them to class tomorrow and you can begin to work on them. And that's it. That is Transformations of Functions, Unit 3, and good luck.